Hi, my name is Brian Cox. I'm an applications engineer for Mitutoyo out of Renton, Washington. And I'm going to be talking about in-process model just-in-time measurements, basically taking an AP242 model-based definition directly from a CAM system and measuring the part based upon that automatically, and also putting the results out into a QIF format so that those can be consumed later. So the problem statement is how to apply an in-process metrology to CAM. What we're doing here is we are taking a model directly created from step NC. It's an AP242 model, it's an in-process model. And what we're going to do is we're going to provide immediate in-process feedback that can be used for data calculation, for tool and part deflections. It'll accurately measure rough and final cuts, accurately verify design features to GD&T, and this gives us an assurance that the finished part will be right the first time with machining optimized, because it will get that feedback loop of the data from the inspection at any point in the process. So the process I'm going to demonstrate here, first we're going to open up an AP242 model into MyCap Planner, and that's going to automatically generate the QIF file. This is a QIF plan that is generated directly from the step file based upon the UUIDs for all characteristics that come across that are basically consumed through the CAD model. And then what we're going to do is just take a positioning, and basically in the CAD that you see there in the bottom right, we're going to position that part in our virtual CMM, basically where we see it in the CMM itself. And then we're going to model some fixturing on the fly and demonstrate how that's going to emulate the system we have. Once we perform the measurements, in real time, the quality data management software that we use called MeasureLink is our software, is going to report out those characteristics based on the UUIDs from the QIF plan, which again got consumed from the AP242 model, and we'll track these UUIDs all across the process, and we'll demonstrate that. We can show how the QIF plan, as well as the QIF results that are generated through our software, keep track of all of the UUIDs for uniformity. So here we go. I'm going to make a demonstration of how to do that. So what we're going to do is import this step model. This step model came directly from step NC, and this is our MyCap Planner software right here. And I'm going to demonstrate what happens here when I open up that CAD model. I first choose a step file, and there it is. I'm going to choose that step file. And I'm going to show that as soon as we open that, right away, there's our QIF file, and that's based upon what you see here, which is the GD&T that was imported directly from the CAM system. So now the next step is to, as I said earlier, we're going to orient this. I could come through here and rotate the part around, but the easiest thing to do is just to mate this bottom surface to the CMM table so that we have the part oriented basically correctly. Now we're just going to position it. I'll start out by centering it in the volume, and then I'm just going to tweak it a little bit to get it basically right where it is on the CMM, basically right around there, and I'll say okay. As soon as I do that, what happens over here on the left-hand side is that all of these characteristics, they were brought in through the PMI, through the GD&T from the CAM system model. They're automatically analyzed, and if I click on one of these, you'll see what our software does is it takes a look at our CMM, it takes a look at that surface and what is needed to inspect that, and it automatically figures out a measurement plan for each individual characteristic. There we go. So the next step, after each of these surfaces over here on the left have been analyzed and we are able to measure them, is to generate a part program I am going to interject one step here that sometimes needs to be done, and that is let's add a collision avoidance zone. What this does, and I'm going to tie this to the part instead of to the CMM, what this does is it says this is a rough estimate of our fixturing, and we're basically going to block out this area from the CMM so that way it's not no collision happens from our fixturing on the system. So that's a rough estimate of what it is. I'm a little conservative there so that I don't have any area where I'm going to collide with the part. The one last step is that when I look at this part, I've already done an alignment on it, which I can demonstrate in a minute how to do, but I am going to tie this position on the CMM to that alignment so that when I actually send this over, when I post this to my CMM, it will take into account the actual position of where that part has been defined and located. But this is a good rough estimate, so I'm going to head and generate a program from this, and that's just this button up here. And what that does is it puts all of those different features that I was looking at earlier into a more complete path for the entire measurement. And this includes probe angle changes, safety moves, and anything that is necessary for the CMM to inspect the entire part from beginning to end. And so you see over here on the right, if I click one of these, they're tracked back not only to the surface that's being inspected, you can also come back here and take a look at the original characteristic. So now that this program's been created, the only step left is to post this to our CMM operation software, and that's simply done with this right here, and there it goes. So now the next step is we're going to run this part and take a look at how that runs on the machine, and look at some of the statistical process control software that we've implemented that tracks this process. Okay, so we're now going to run this program that I posted over here. This is the program that just came from the same name of the file that we had. And I will open this up. And we're just going to run the latest execution of this. There are a couple of warnings that pop up. And now, because we had originally, as I said, we had done an alignment manually on this machine to tell the part, to tell the computer basically where that part is more specifically in space. There's nothing else we need to do. The entire program will run, and when we get to our first characteristic, what will happen is our statistical process control, or actually quality data management software, will pop up, and in real time it will track the UUIDs that were imported from the CAD model, and we'll see that here in just a moment. So this launches our quality data management software, and that's just off screen here. I'll bring that right back over. There we go. And you can see we've run this program several times already, and now as we measure additional features that have been toleranced, you'll see that this is populated, and every one of these is exactly as it was written in the program originally for step in C, and all that data is carried forward. There are some mistakes on this particular program. You'll see that these diameters are far off. The wrong number was input for the nominal diameter of these features, but you can see if we look across, it's fairly consistent, and it just tracks everything that was brought forward. So while that's running on the machine, I'm going to talk a little bit more about the MyCap Planner software that generated the solution. As you see here, all of the PMI was brought in from the from the CAM system model, the in-process model, and you can clearly see that if I click on any of these, they're tied to certain features. But if a feature is not has not been toleranced previously, you do have the ability to come in and just right-click on a feature, say add this as a plane. When I do that, I can then also add it as a characteristic to that plane. I can say I want a flatness GD&T call out, and over here in the tree, you can then come in and edit that as well and say, well, let's make that a 0.05. And now we have a flatness. We can do that, of course, with any other characteristic, such as parallelism, perpendicularity, and so forth. It's going to give an error on this one because obviously we're not parallel to B, we're perpendicular to B. But this is one of the features of the software, is it does catch some of your errors in GD&T and allow you to know if something does not make sense and cannot be measured accurately, or if it doesn't represent the model accurately. The other thing I had done earlier is I had performed a manual alignment on that part that's running on the CMM right now. And to do that, there is a section up here in the tree at the top called manual alignment. There's also a CNC alignment. They both basically work the same way. The way I do this is I just right-click on the feature that I want to add to a manual alignment, and I say add this feature to manual alignment. When I do that, you'll see it throws it over here in the tree. I now have a red manual alignment section, and the reason it's turned red is to let you know that not all 6 degrees of freedom have been defined by this alignment. More data is going to be needed by the CMM. So I will come in and I'll keep adding other features. I'll add this to the manual alignment, and I'll add this to the manual alignment. Oh, pardon me for 1 second. That's the results. Let's go back here. Add this to the manual alignment. And as soon as I add that third feature, you'll notice this turns black, and you can actually see every degree of freedom that's being defined by each of the features you've selected. And if I click through these and look at the properties, I can see that, for example, this plane here is a 4-point measurement. It's going to use this angle. I can change any of this up if I'd like. But it also pops up a little picture down here. And this picture will be presented to anyone who's going to run this manual alignment so that they know what feature to align. And if I click through here, there's another 4-point alignment and another 4-point alignment. And how to actually run that program has already been defined, and it'll walk the user through that to get an accurate alignment on that. So that's all that has happened. If you notice, this had popped up in the end here. This is just a typical PDF of a standard report format that we typically use. But what I want to demonstrate is that as I ran that part, this one here was actually the last run that we ran just now. This was a previous run that was incomplete. But it has processed all of that, and again, everything is tied to UUIDs directly consumed from the CAM system. I can then take this and I can export this results with the statistics and all into a format of a QIF, another QIF format, and this will be QIF results. I will browse to the same location I have my other QIF plan, and I'll call this the same name. But I'll add to it the results. And while I'm here, I'll also rename this. And we'll call this the plan. Okay, and then I'll export this. Now, while that's running, what I'm going to do is bring these back up. I will open up first. I guess I didn't. Oh, okay, I didn't rename that properly. But this is actually the results. This is the plan. And if I open these side by side, what I like to demonstrate is just that, as I said earlier, the UUIDs are carried forward. Here is the part UUID on this one. If I come over here to the other, this is on our results, we can see the same UUID there, and the same is true of the characteristics. If I go to my characteristic items, here with perpendicularity, there's one UID. And just to demonstrate, everything is tracked all throughout the process. All features have been properly labeled with the same UID. And now a QIF reader that is hopefully being developed pretty soon in this new standard would be able to present this and track this throughout the process.